So I'm Neil, and I'm here to talk to you about data pipelines for operational metrics. So first up, I just want to say I don't work for any company that I mentioned on these slides other than OM1. I don't have any vested interests in either. I've tried to keep things as generic as possible, but I do lean into a few open source technologies, so we'll talk about those a bit more. As the intro was, I'm VP of Engineering at OM1. We're an 8-year-old healthcare data company, and we try to make data-driven decisions wherever possible. And this presentation is based on the work we've done at OM1 to get our operational metrics into shape. And we've used those to make decisions on investments, process improvements, budgets, etc. All right, so first thing I'm going to cover is a bunch of concepts to make sure we're all on the same page. Some of these you already know. Some of them you've heard of and probably have an opinion about what they are in your head. But I think it's good for us to kind of go through these and make sure we're all on the same page. So first up, a data lake. This definition actually took off Google, but I'll just read it out. So a data lake is a centralized repository designed to store, process, and secure large amounts of structured, semi-structured, and unstructured data. It can store data in its native format and process any variety of it, ignoring size limits. A data lake provides a scalable and secure platform that allows enterprises to ingest any data from any system at any speed, even if the data comes from on-prem, cloud systems, or edge computing systems. It can store any type of volume in full fidelity, process data in real time or batch mode, and analyze data using SQL, Python, R, or any other language, third-party, or analytics application. So, data lake. Next up is a data warehouse. Probably heard of this as well. It's an enterprise system used for the analysis and reporting of structured and semi-structured data, which we get from multiple sources, such as point-of-sale transactions, marketing automation, customer relationship management, and more. A data warehouse is suited for ad hoc analysis as well as custom reporting. A data warehouse can store both current and historical data in one place. It's designed to give a long-range view of data over time, making it a primary component of business intelligence. So let's compare these two. I'm going to look at them side by side across a few criteria. So data warehouses are storing structured data. Data lakes are storing structured, semi-structured, and unstructured data. Talk about processing of data. In a data warehouse, you need to put the data in a defined particular schema. So you've got to understand your data and put it in a particular way. This process is known as schema on write, whereas a data lake, you can put it in any format you want. It doesn't matter. Unstructured data, semi-structured, however, if you want to read that data, then you need to apply a schema and understand the data at that point of read. This is known as schema on read. Storage. Data lakes are cheap to store stuff. Data warehouses can get expensive, especially when you start getting up into petabytes. Agility, so if you want to make a change to a data warehouse, because of the structured nature of the data and the way that a lot of things depend upon that schema, it's hard to make changes. It's difficult to come in and go, I'm just going to break apart this table and reformat it. No, you're going to just break downstream things. Whereas in a data lake, you can just go in and change structures of things because the person consuming that data has to understand the schema. And lastly, let's talk about maturity first. So data lakes maturing, data warehouse has been around a while. Let's talk about users. Typically, a data warehouse is used by business professionals. People can go in there and they can run their own queries, understand the data. Whereas if you've got people like data scientists or engineers who are much more savvy with the unstructured nature of a data lake, can go in and pull out the data that they want. So we also have another option. It's very unimaginatively called a data lake house. Take the best parts of a data warehouse and a data lake, smush them together, and you've got a lake house. It combines flexibility of the cost efficiency of a data lake, but you then have this data management processes that you have in a data warehouse. So if you look at this slide here, you'll see in the middle section, this is how traditionally you would have worked with the two things together. You'd have had your data in data lake, you'd go through some sort of ETL process to get it out. into your data warehouse to do some sort of data processing and deliver some insights through your BI reporting engine. When you've got a data lakehouse, you can just do all of that within your lakehouse. So here are examples from lakehouses. Your favorite cloud vendor has their own. Your less favorite cloud vendor probably has their own as well. There's also some well-known players here in the market. We happen to use Snowflake, but you can, if you're let's say, wanting to go with something more open source, you could use Presto, and Starburst is actually a paid implementation of Presto. Final concept we can go over is ETL and ELT. I assume everyone's heard of ETL. It's extract, transform, and load. And this involves transforming data on a separate processing server before you put it in a data warehouse. So in the ETL tool, you typically got some obscure language that you've got to write your transformation logic in, and then that data is put into the warehouse. On the other hand, ELT is extract, load, transform, and that basically performs the transformations directly in the data warehouse itself. And it's it's replacing ETL more and more. So now I've covered some concepts. Let's start talking about some of the operational data we want to analyze and understand and run through our pipelines. So here are many, many technologies used by us who are versed in the dark arts of DevOps. If you look on here, you can poke around. You'll be like, yep, I recognize a bunch of these technologies. You're going to use pretty much one in every box. Those out there who are unfortunate enough to be in large companies have multiple ones in the same box. These are all generating useful data that we want access to understand and use to make business decisions around. So let's talk about how we do that. So first up, let's go about the problem. So we have all this data that's everywhere in those boxes. They are very siloed within those systems. The problem with that is that because they're siloed in there, we can't really link it across. And often these systems, they don't keep enough history around. You can look back and go, okay, well, I've got this log data, I've only got it for 30 days because that's all I can afford to keep it in my SIM. The data doesn't join easily across the systems. So if you want to get your cloud cost data by an engineering team, pull that in somewhere and do analysis on it, you've got to jump through some hoops. And if you want to answer some sort of business questions or strategic questions, right now you're probably going to these systems, pulling data out, stuffing in a spreadsheet, maybe running some scripts to pull it out, having these complex Google Sheets out there. And then someone will ask you a question and you'll have to go off into the system again, pull out more data, do analysis. And then next month rolls around and someone else asks you a question. You're like, damn it, how the hell did I do that analysis again? And if somebody leaves and you inherit these spreadsheets, it's a nightmare trying to keep on top of all this data. In essence, basically what we have, what I like to call an operational data swamp. No mosquitoes, no gators. Data swamp also comes with a fine lakehouse, real fine, although around here that still cost an arm and a leg because it's Boston. All right, so why do I call it swamp? It's siloed. You can only, you're in a swamp, you're kind of stuck in that part of the swamp and you can't get around easily. It's not linked up. Your commit histories in GitHub, you can't combine that easily with your CloudTrail logs in AWS or your issue details in Jira. You're relying on the reporting of the system you're in. So you can go into GitHub and see all this wonderful list of how many lines of code someone has deleted, but you can't necessarily combine that with something else. But some of you are going to say, hey, I got a SIM, I'm great, I got all my data in one place already. Yes, but anytime you want to do any analysis in there, you're using some proprietary language. And typically, not everyone has access to that. So you're kind of having to go in there and write your own queries, and no one else is going to do that because they don't know the language of it. If it's in your SIM, you might have a limited history. And performing analysis across different sources is hard. It's kind of hard to combine the data in the SIM. And you've got this non-standard schemas, and there's definitely no documentation around what data's coming in and how it's structured in there. You got to kind of figure it all out for yourself. So in summary, hard to navigate, limited history. It's really hard to democratize access to this data. So let's talk about our goals. Right. I mentioned the last slide, data democratization. We want to get this data into the hands of everybody. All this operational data we've got sloshing around in our org. We need to have a single source of truth to be used for our reporting. Right? I've had this before where somebody puts up some numbers and someone else has got the numbers across the same thing and they're different. Like, let's have one source of truth. You can't start reporting different numbers for the same thing. We need a standardized language to inspect the data. All these different systems use different query languages. No, we want one, and we want to be able to link across our sources. So we can combine our GitHub data with our Jira data with our cloud cost data. We want to provide dashboards and visualizations, and we want accessible to all. Right, I don't know if I think I might be being a bit unreasonable, but I think we can do all this. Few things to note, things that are not in scope here. We're not replacing existing monitoring systems. Right? If you have a nice SIM that's giving you, lots of interesting metrics and logging data, you still need that to diagnose and figure out what's going wrong with your production problems right now. But if you want to go back in time and look historically over 6 months, that's not the system you should be using. All right, so how do we do this? If you want your executive summary, this is what it is. Take all that data, somehow stuff it in your lakehouse, do something, generate reports, profit. There you go, we've done it. Really though, how does that come through? Let's look at the fancy red pipes of our data pipeline and how this all ties together. So, it's essentially going to be 5 steps we're going to go through. We're going to identify the data we want. Then we're going to load that data extract that data out, and for that we've got to figure out, how are we going to get it out? And then we're going to load it up into our nice, shiny lakehouse, make that data understandable by all by doing a series of transformations to get it into a standard shape that people understand and link the data together. And once that's all been sort of normalized into a standard schema, we can then start building some reporting and some dashboards on top of that. Make it all explorable by all and available to all so people can look at the data. So, identifying data sources. If we were to go back to that slide where it had all the big box of all the different icons on it, you should be looking at those and thinking to yourself, okay, what systems do I need to be pulling my data out of? And if you don't know which ones you want to think about how you're going to be using that data. Like, are you looking to try and sort of modify behaviors in your org, right? Or am I looking for, better planning, better budgeting? Am I looking to identify places where I can, implement some efficiencies? Am I looking for process improvements? Think about what data you need based upon what it is you're trying to achieve. Once you're thinking about that, think about, well, what data do I need to drive my reports? And another thing to think about is that the data that you're looking for could come from multiple sources. So if, let's say, you're wanting to capture your unit test results that are being run in your CI/CD pipeline, you can probably get that data from either out of your logs from your CI/CD pipeline, or you may be getting it from wherever the results of your test cases are getting published to. If you have a SIM, you can capture a lot of data from there. Anyway, a lot of the SIMs out there have native integration into a data lake anyway, via an S3 bucket. Another thing to note here is when we're looking what data to bring in, start small. And I mean small in terms of both the number of data sources and the amount of data you bring in for each source. Don't go there, okay, I'm going to bring in 10 years of ELB logs. Let's do that as your first thing. Don't do that, that'll be bad. Start with 3 months, bring the data in that way, and start with a small number of sources, get it running through the pipeline, then bring in more. So, extract and load. You may notice I've smushed 2 steps together, and we're doing ELT. So there's a few ways you can do this. So there's the box of all our massive data sources again. If you have some sort of native way via your cloud storage system to get into Data Lakehouse, use that. For example, we have your AWS costs or whatever your cloud costs are, you can probably just put those costs straight in a bucket and have that load straight up into your lakehouse. I have a technology on the slide here called Airbyte. Has anybody here used Airbyte? Heard of Airbyte? There's a few of you. Good. So Airbyte we use here to perform the extract and load part of our pipeline. It's an open source tool, and I will dig into that a little bit more now. So Airbyte calls itself an ETL tool. I think of it as an EL tool. The transformation piece is not the best part of it. What is the best part of it is that it's open source, and it has over 350 official connectors. So Airbyte will connect into a lot of different systems you've got and pull the data out from there, and then you can connect it up to whatever you want to put your data into, whether it be your lakehouse or if you have a data warehouse. These connectors run using Docker containers, and you can orchestrate your whole sort of Airbyte connecting and pulling in using like an orchestration engine like Airflow. There's also a toolkit to build your own. We have built a few of our own connectors into systems that didn't have them already. And they launched a Terraform provider. So you can now start defining all this loading up of data through code. And then if you want to pay for a SaaS version, it's there, but we don't. There's other alternatives out there, Stitch Data, Fivetran. But the idea is that you want something to get that data, pull it out, and stuff it in to your data lakehouse. All right, extraction load 101. We want to be loading the raw data. So don't be tempted to do some transformations as you're too early. If you've got your raw data in there, you can do the transformations cleanly and easily in your data lakehouse. So just ship the data in as it is. We can do the transformations later. If you're loading data that represents the state of a system and doesn't have a history, such that you can look back and see how that system changed over time, you want to do full loads on a known cadence, so let's say weekly. That way you can then have a full history and look back in time within your data warehouse to see how a system has changed. For an example for this could be, let's just say you have a system that is doing vulnerability scanning and gives you a snapshot of all your libraries and their current set of vulnerabilities they've got. If you pull the full set of data out weekly, you want to pull it in and load it up for every week, because then you can go back in time. I call this the lake versus warehouse trade-off as well. Sometimes you want to bring data in that's been pre-aggregated. You don't want to necessarily ship all your logs in for all the things. So I'll use load balancer logs as an example. What you really want to be doing is bringing in metrics that have been defined by your logs. So you want to bring in things like, how many errors happened over a course of a minute, an hour, whatever you've defined, and ship those logs in. Otherwise, you'll be bringing in a lot of data. So you can use your SIM often to do this by pre-aggregating your logs and then shipping them over. Nothing to be aware of is getting throttled. GitHub API is slow, and it loves to throttle you. You really got to think about ways to hit your systems in a way that doesn't actually affect the performance of those systems as they're running. GitHub is a particular bane of our existence when it comes to throttling things, because their API is slow. All right, so their M1 implementation. You can see all the things that we're pulling in here. Jira data, GitHub data, Mend, that's what we use for vulnerabilities, third-party libraries and their versions, licenses, etc. Our Okta is an interesting one, because we actually pull in all our Okta data around what groups we have within there. So that way we can define what engineers are in what teams on any particular point in time. We keep that historical data. So when we're planning out capacity planning and looking back historically when teams have been, how much they have produced over time, we can actually use the Okta data to see how many people are on a team. We have 15.5 here. You'll be like, whoa, 15.5, that's an HR system. Why are you pulling that in? We have our corporate goals in there. We have this team pulse that measures how well people are feeling at work that week, and that's a good data point to have in when it comes to dashboards. A few other things to note here. We have data.world. That's our data catalog. We put some data in there that's metadata. It's useful. We also connect back into that later on. A few things to note, we push things through our sim, comes through nicely using a S3 bucket. I really recommend this approach. It's super easy to set up, and data can flow in pretty easily, and you can set your sim up to aggregate certain logs, generate metrics, and ship those. And of course, cost data. So we have our AWS cost data, our Databricks cost data, and other data as well that just goes straight into our native bucket. And then we load it up all as raw data into Snowflake. So we've got this data in there. It's all raw. It's a bit of a mess. How do we get this into this nice structured set of tables so we can actually report on it? We use a technology called dbt. It's another open source technology. And dbt will manage getting this set of raw data into structured normalized tables. Essentially does it using a set of queries, SQL queries, and I'll go through that in the next slide. So dbt stands for Data Build Tool. It is an open source data transformation workflow tool. Their words, not mine. Essentially, dbt allows you to write SQL transformations on data. So now we've got all our data into our data lakehouse. We can now finally use a common language to actually query all that data that's in there. And dbt is the tool that allows us to then execute a series of transformations to get the data into a standard format. So dbt will manage the whole DAG of stage transformations because you're going to write SQL queries that will modify your data, and of course you end up with this massive sort of graph of transformations that need to get run in a particular order, and dbt will take care of that for you. It also handles materializations. You just focus on writing select statements. There's a few other things that are useful, like adding seed data. So we add various bits of seed data that we can't pull in easily from elsewhere. It has reusable models and macros, which allow you to more easily define your code and keep it dry. It supports two ways you can process your data, full and incremental. So a full processing, you're going to load all your data at once, and incremental processing will identify new data that has shown up that it needs to transform, and it will only run against that. One of the great things about dbt is as you're actually working with it, if you change your model, it will figure out what it needs to run based upon what model has changed in its dependencies. It has a built-in series of data quality tests, and you can use existing source control and CI/CD processes as part of you building out your dbt models. Basically, it will produce a container that runs a series of SQL queries that you can just execute in your data lakehouse. So what does it look like? This is probably going to look terrible on the screen. A model is up on the top right here. It's basically a blueprint of a table. You write it in SQL with Ginger templates. So in this one here, we're just referring back to a model called stage GitHub pull requests and stage GitHub repositories. And this model here is just basically identifying which PRs are in a default branch. The second one down, you can see we have an example of some seed data. I wanted to dump in the end-of-life dates for Python runtimes. Because we have a bunch of Python stuff, I want to know what projects have got end-of-life dates coming up. And this bottom one here is a macro. That's an example of a macro that we use. So Jira is inconsistent in how it actually formats its dates when you export data out of Jira. So this here is a bit of a convoluted way in which that it will figure out how to pass the timestamps that come out of Jira to produce a consistent timestamp regardless of what object you're inspecting. So when you're transforming your data, there's essentially 3 steps you go through. The first step is staging. Basically, you build a model that represents your raw data. So if you bring in a set of raw pull requests out of GitHub, you will have a model for staging pull requests. The next stage that you go through is the intermediate step. This is where you're building all your transformations to get your data into the format you want. And then your final level is your marts, which is your nice curated set of data that is a good final representation of the data that everyone is going to work with. Typically, this is where all your end users are going to do their work and investigating the data. Not usually. They will have to go back to the intermediate, but sometimes they may have to go back to the intermediates to try and get some data that you forgot to pull through. So, a few things to note about transformation. Probably the most important thing is make sure that you have metadata to link your models together. So you want either some sort of seed data that you can bring in that will help tie things together, or you tag your resources in one of the ways you can. So for example, with all our AWS resources that we have, we tag everything in using Terraform default tags with what repo created that object. And then in GitHub, we actually tag each GitHub repo with which team is responsible for maintaining that repo. So that way we can now tag through a resource, a piece of AWS cost, we can tag it all the way through to the team that is responsible for the resource that incurred that cost. So dbt also enables you to have data quality tests. You want to put testing in with every model you have in your pipeline. The earlier you can capture errors in your data, the better. So you can put tests in that checking that, okay, a field's not null, that should not be null, key constraints, data ranges, etc. Another thing to note as well is that if you have a particularly slow-running query, think about how to materialize that, because subsequent queries don't want to be querying a slow view. Example is if you're doing like a distinct select query over a large set of data. All right, last step. So we now have this wonderful schema of all our data that we care about. It's beautifully linked across. How am I going to report upon it? So there's a lot of reporting technologies out there. Everything from all your sort of cloud-native ones like QuickSight in AWS, you have Tableau. There's another system, you have things like Streamlit as well. There's many technologies out there. Your org will have a lot available. Because everything's in SQL, you can use so many different tools now to report upon your data. So use what you have is basically what I'm trying to say here. However, there's a few rules you want to think about when you're selecting your technology. You want to make it easy for your power users to build their own dashboards. You also want to provide standard dashboards. And you want to make sure that any dashboards that are getting built are actually getting managed using software development processes. So you want to be able to define them as code. You want to be able to check them into the same repo. You want to have a notion of a dev environment for your dashboard so you can build new dashboards, make schema changes without breaking what is in production. So talking about schema, you're going to want to document your schema so people can actually use this data. So they go in there and they're like, what is this cost data? What does this mean? dbt can help you generate your documentation as you build it. So use it. All right, so let's talk about some of the reports that we generate. I didn't put any charts up here because I didn't want to be putting up here how many ridiculous amount of money we spend on things like AWS and Snowflake. But these are some good reports that we use. So cloud budgets, that's a good one that people care about. Are we on budget? Are we spending too much? Are we spending too little? I have this chart, I call it the worm. It's basically a line going up with your daily spend, and if you're going above it, you'll see your line going above the worm, and if you're below budget, you'll be behind it. Cloud costs, if you've tagged your data well by tagging it by your product, your team, etc., you want to be and linked appropriately, you can now start really cutting your costs. So cutting your categories by whatever category, cutting your cost by whatever category you want. So in our case, we actually cut it by okay, this cost is generated by this service, this repo generates this cost, etc. A few other ones that are interesting, agile planning. People often want to know, how well are my teams planning this stuff out? How predictable are they? So we have all this data now. We can actually start displaying things like velocity by sprint over time, committed versus actual in terms of points, and looking at standard deviation of velocity. Are people consistently hitting the same sort of numbers? We like to see our teams plan out 1 or 2 sprints in advance so we can see how well their pipeline of work is coming through. So we'll have dashboards to sort of represent all of this. Understanding how many stories are completed within the sprint, and then also things like P1, P2 issues meeting their SLA. A few other things, I like to call this service care and feeding. Really want to understand right now what's going on with your services. do I have any upcoming end of lives? What's my vulnerabilities? What's my risk score associated with services? Being able to plot all that out. My coding machinery, how fast are things moving? How well are they moving? So build times over time. Another good one as well is of my builds, what's the percentage that's passing and failing over time? And also median PR time is a good one as well for repos. And then of course, if you've managed to aggregate up some of your metrics around your app performance, you can pull all this in as well. And again, you're going to want to look at your certain metrics that you want to have a look back at a historical point of view. So is my latency over time, is it going up or down? What's my percentile of my responses that are coming back within pick your time? And error rates over time is another one. A few other things to note. You want to create customized dashboards for your teams. Your infra team, for example, is going to want to have a different set of dashboards than your web apps team. So think about the needs for each team. We have an executive dashboard as well that we present on a monthly basis to the executive team around the state of the engineering org. And it's great. It just auto comes up. No spreadsheets needed. Another useful thing of this, once you've got all this data flowing through, you can use it to generate models to predict future costs or anything else you want to predict out of the future. For example, with finance, we've got to the point now where no one in engineering has to do timesheets anymore, even when they're working on custom work, because we can track it all through Jira. Engineers like that a lot. And we can also track our software capitalization costs. DORA metrics. Once you got all this data in, it's pretty easy to do your DORA metrics. So there's a few things you'll need to think about, like doing deployment frequency. You got to think about, okay, what bucket am I doing it daily, weekly, or monthly? My deployment frequencies. You just got to think about doing the median number of days that you do a deployment, and if you're above 3, then you can say you're daily. Lead time for changing. You've got your Git data, you've got your releases. You can do that. Change failure rate, as long as you're pulling in your deployment data and your incident data, you can now again track it easily there. Same with time to restore service. As long as you can link this data together, you'll have all this to do your DORA metrics. All right, so the view from the OM1 operational data lakehouse. It looks nice. It's only better than that swamp earlier. These are basically our learnings that from doing this. The big one, I will keep banging the drum on this one, is you got to link your data together. Once you've got the data linked together, once you get into that data warehouse, combined together, you can really get some good reports together. Another one that I like is make sure that all your pull requests have your Jira tickets or whatever you're using for your issue tracking. We have a GitHub action, it's not a GitHub action, it's actually a Lambda, that enforces that every pull request must have a Jira ticket that's open. Tempting to dump all your data, just use your SIM, filter it down. It's not a replacement for your SIM. Another good one here is carrot and stick. Like if you're rolling this out, work with certain teams who are going to be more responsive to this, get them working well, then try and get other teams to do it, and then you can start using the stick. A few things, put everything in the same repo, so you can make one pull request to change your pipeline end to end. Crap in, crap out, obviously, everybody knows that. And write lots of tests. A few things, get dashboards reviews as part of your team ceremonies. Have them look at their dashboards regularly, because that will then they can make quick behavior changes as needed. You're going to want a dashboard for your pipeline, a bit Inception-like, but you're going to want one. And you're also going to want dashboards for your data quality, so people can make sure that the data coming in is of high quality. Schema migrations are a pain to manage, real pain. They will break things. You'll have to have a process to manage that. And if you're documenting your schema, people will find it more useful. And the last one is, if you can orchestrate it all up with Airflow, all will be good. Lastly, what have we not put in? We do have HR data in there, but a very small amount. It's not individual data. I don't want any HR data getting seen by people that shouldn't be seeing it. So we really restricted it down to just some aggregates. Things like, corporate goals, pulse scores, high fives, etc. And that is all. And I am bang on 35 minutes.